Hi class. So far in this unit, we have learned how to get vector and parametric equations of a line, the Cartesian equation of a line, and then vector and parametric equations of a plane. So it should be no surprise that now we're doing the Cartesian equation of a plane. Okay, so what we're going to do here is learn how to do that. So obviously, Mrs. Weens, that's what we're doing. Okay, verbal issues today. Let me just get my pen and hopefully it will be better. Okay, so the Cartesian equation of a line is ax plus by plus c equals 0. And in that case, the normal is equal to AB. Okay, so what's different about a plane than a line? Well, a plane has 2 dimensions, okay? So it actually has a normal axis, okay? So for any plane in R3, so we can call this pi. Now I attempted to draw this. This is supposed to be one line going through, okay? It's just going from under and through. And imagine that it is going through it at a right angle, okay? So the normal axis is the one possible line that can be drawn perpendicular to the plane through the origin. Okay, so any non-zero vector on the plane can be the normal, which we call n. Okay, and so that can be defined anywhere on the normal axis, and we'll call it A, B, C. Okay, so there are an infinite number of collinear n. Okay, so again, a normal, in this case, will cut through the plane at a 90-degree angle. So let's develop, using that, we're going to develop the formula for a plane, the Cartesian formula. So imagine when we have a plane here, again, we call planes pi. So we just put pi kind of in the upper corner. And we have a line here on the plane. So let PO be any specific point that we're given. So we'll call that XO, YO, ZO. Okay, and then we'll say let P be any generic or any other point on the plane. So we can call that point P, and we'll just call it X, Y, Z. Okay, then we can draw a vector, a position vector, 0P, OP, so coming up from the origin, and then we can dot it to show it's kind of behind the plane there. All right, and we can also draw a vector RO, so going from O to PO, like that. Okay, and then the normal cuts through the plane at 90 degrees. So we'll label that the normal. So it's going at 90 degrees, and we will define its coordinates as A, B, and C. Okay, so that just gives you a setup there for what I'm about to do. So from PO to P, I can create the vector PO to P by doing X minus XO, Y minus YO, and Z minus ZO. Okay, so the normal is ABC. Okay, so we know that the normal dotted with the vector POP has to be 0, since this, the normal has to be perpendicular to that vector. So if we take A, B, C, and we dot it with X minus XO, Y minus YO, Z minus ZO, and set it equal to 0, we can actually go through and do these calculations and come up with the Cartesian equation. So when we do this, it can be rearranged to AX plus BY plus CZ minus AXO plus BYO plus CZO equals 0. Now, if you're a little bit confused, you can go back to the Cartesian equation of a line. It's similar to this. These are all constants. And we're just going to say that we'll let this equal D, capital D. Okay, so now we say the Cartesian equation of a plane.
Pardon the interruption. Intramural players, go to the big gym. It's too soggy outside. There's standing water. So if you're involved in intramurals, head to the gym. Good luck, everyone. 4 and 3 play first, followed by 1 and 5 at 12:10. Got it. All right, thank you.
All right, not awkward at all. All right, well, for those of you watching the video this year, you'll know what that was about, but in later years, you'll be like, what in the world was going on? Anywho, so you can just let all these constants be D, and then you get your Cartesian equation, AX plus BY plus CZ plus D equals 0. So it's very similar to the Cartesian equation of a line. It's just that we have an added term here because our normal is in 3 space. Okay, so this is so what also is important to understand, hopefully you have some more room, is to realize that this is a non-zero vector. And get this is important. It's perpendicular to all vectors on the plane. Okay, so any vector on the plane will be perpendicular to that. So that is good because that will help you. That means the dot product between the normal and any vector on the plane is equal to 0. Okay, so let's go through some examples. So the point 1, 2, 2 is on a plane that has a normal, that should have a vector, with a normal of -1, 2, 6, determine the Cartesian equation of the plane. Well, we can just start with, okay, we start with AX plus BY plus CZ plus D equals 0. And we can say that A is equal to -1, B is equal to 2, and C is equal to 6, since those are equivalent to the normal. And then we can just let X be 1, Y be 2, and Z be 2. Okay, because that's the point. And then these will all be filled in. We'll only have an unknown D, and we can solve for 0. So this is -1 times 1 plus 2 times 2 plus 6 times 2 plus D equals 0. So you solve this and you get D equals -15. Now notice if you put this in originally, you would get -X plus 2Y plus 6Z minus 15 equals 0. But think about why I don't like this and why mathematically this isn't great. Okay, so for Cartesian equations, your leading coefficient should be positive. Okay, so you could just multiply this by -1 and get X minus 2Y minus 6Z plus 15 equals 0. And that would be the best answer. Okay, so now what if we're given 3 points? How can we find out the Cartesian equation? Well, what we need is a point and a normal, like we were given in equation 1. So clearly we have 3 points, but we need a normal. But guess what? The normal, because it's perpendicular to the plane, that's just the cross product between 2 of the direction vectors, okay? Because the 2 direction vectors give the direction of the plane. So the cross product is that vector that's perpendicular to both of those vectors. So, cool, huh? So now we just need to find 2 direction vectors, AB and AC, and then we'll cross them. So AB, I'm assuming you guys know how to do this by now. You do B minus A. So you get 4, 0, -1. And AC, you get -1, -5, 1. So think about it. These are 2 vectors on pi, so on the plane. So cross product will find the normal. So we take AB and we cross it with AC. Okay, so if you remember how to do that, then you do AB, so you start with the second one. So 0, -1, 4, 0, and then you set up AC, -5, 1, -1, -5, and then you do the whole crossing and subtracting thing. So you get, in this case, when you do the cross product, -5 for x, -3 for y, and -20 for z. Now, because this is the normal, actually I should have put normal is equal to this, we can scale it to 5, 3, 20. Okay, since the normals can be collinear. All right. So that's what A, B, and C now are in the equation. So therefore, we would have 5x plus 3y plus 20z plus d equals 0. So now we can sub in any of these 3 points. It doesn't matter which one, and we can solve for d. So I subbed in A, and you can solve for d, and you get that d is equal to -101. So your final solution then is 5x plus 3y plus 20z minus 101 equals 0. Okay, now let's move on to example 3. Okay, so given this line, okay, oh, sorry, not the line. This is the vector equation of a plane. So if you're given the vector equation, how can you determine the Cartesian equation? Well, in the Cartesian equation, you are given the two direction vectors. So the normal then would be the cross product between the two direction vectors. Okay, so you would be taking 1, 0, 2 and crossing it with -1, 3, 4. Okay, and that results into 2, -1 when you do that and scale it. Okay, so then you can just sub in 1, 2, -1 into 2x plus 2y minus z plus d equals 0, because this is a point that we know is on the plane. And so when you solve this, you get d is equal to -7, and your final answer is 2x plus 2y minus z minus 7 equals 0. Okay, example 4 is a little bit trickier. I'll try to take a bit more time with it. So imagine we have Cartesian equation, but we want it the vector equation. So here is our vector equation, Cartesian equation. Okay, we're going to rewrite it in as x equals. So we're going to put x equals 2y minus 5z plus 6. Okay, so what we're going to do is find 3 coordinates on the plane. All right, so we're just going to find 3 coordinates on the plane. Any 3 coordinates that are on the plane, we're going to choose values for y and z and then solve for x using this. Okay, and then we'll write the resulting point. So if we let y and z both be 0, that's the easiest, then x is equal to 6, and we have a coordinate 6, 0, 0. If we let y be 0 and z be 1, you can solve for this. You get that x is equal to 1, so you get the coordinate 1, 0, 1. And if you let y be 1 and z be 0, you get x is equal to 8. So x is 8, y is 1, z is 0. So we're going to let these points then, I'm just going to call them, I called them A, B, and C, but that's a little bit confusing. How about I call them P, Q, and R? Okay, so now that I know 3 coordinates on the plane, I can create 2 direction vectors and use one of the coordinates for my vector equation. So we're going to create 2 direction vectors. Okay, so the first one, I'm going to do PR. Okay, so if you do PR, you get 8 minus 6, 1 minus 0, and 0 minus 0. So you get 2, 1, 0. And then I'm going to do QR as my second direction vector. And you get 7, 1, negative 1. Okay, so then you can write your vector equation. So all I need here is one of these points. Okay, I'll pick 6, 0, 0. Now, remember, you can't scale the points that are on the plane. This is a point that's on the plane. So I can't all of a sudden say that 1, 0, 0 is on the plane. That doesn't make sense. It's only the direction vectors that you can scale back because they just give the direction. They're not necessarily on the plane. So then I have a parameter in front of my first direction vector, which is in simplest form. And then I have a parameter in front of my next direction vector, which is also in simplest form. And I say that S and T are in the set of all real numbers. Okay, so you could check if this is right by converting it back into Cartesian form if you'd like. Okay, finally, just some facts. Okay, these aren't really examples, but just some facts for you. So I tried to do this the best I could. Okay, it's really hard on the trackpad. I'm sure you're making fun of me. Thanks, guys. So if you have 2 planes that are perpendicular, that means that their normals will be perpendicular as well. So this is the normal to plane 2, and this is the normal to plane 1. So normals will have a dot product of 0. Now, if you have 2 parallel planes, so here's the normal of the first one, of plane 1, and here's the normal of the second one, plane 2, then these will be parallel. They will be, scalar multiples of each other if the planes are parallel. Finally, one last thing. If you have 2 planes that intersect, not necessarily at a 90-degree angle, think about it. The angle between the 2 planes is the same as the angle between the normals. So even though the normals are perpendicular, so this one would have a normal that looks kind of like this, and this one would have a normal that looks kind of like that. So this is normal for 2, this is the normal for 1. The angle between them, theta, is the same as the angle between the 2 planes. So we can use our formula from last unit. So it's the dot product of the 2 normals divided by the product of their magnitudes to find the angle between 2 intersecting planes. Cool, huh? I'm such a great artist. I should really reconsider my career. Anyways, thanks for watching, guys. Hope you learned lots.